Okay. So let's continue the lecture 1 from last time. Last time we introduced summary statistics and also the discrete random variable, continuous random variables. And today I will talk about the linear function of random variables. Then we go to the normal distribution in the lecture 2. After the normal distribution, I will discuss the binomial distribution. If we still have time, I will go through the Poisson distribution. And we definitely no time for hypergeometric distribution. So for that part, we will move to lecture 5. And for Poisson distribution, it depends on the progress today. Okay, so let's start. So we can see for the random variables, we normally use a capital letter. And here, capital letter X is a random variable. And capital Z is a linear function of this random variable. So we can see if the new random variable Z is the linear function of another random variable X, then the average of Z has some connection, it's a linear connection to the variable of X. So if I write a notation mu of Z, so this is the average of Z. And we can replace Z by AX plus B. So this means Z is a linear function of X with the coefficients A and B. And after that, we can see mu Z actually equals the constant A times the average of a random variable X plus another constant B. And definitely we can prove it, and here I will skip it because I will never test the proof. It's not a math, so we are more focused on the application. And for the sigma square, we can know the variance of the new random variable Z is the A square. So for the variance, it only relates to A. It is independent to constant B. So if we take a square root out, and for the standard deviation, because A could be positive or negative, so we need to take absolutely value for constant A. So the standard deviation of a new random variable Z is the linear function of the standard deviation of a random variable X. Okay? So this is easy to understand. If we just shift all your random variable by a constant, then definitely we get a new random variable, and the average just shifted by constant. And if we times it by another constant, then that means we just change the unit. For example, if we want to measure the weight, the height, we can either in meter or in centimeter, right? Then it's just different by 100. So this is easy to understand. And then we move to two independent random variables. X and Y are two independent random variables. If they just get the linear combination, like we get a new random variable equals X plus Y, one random variable plus another, or the new random variable is one random variable minus another one, then we can see the average of the new random variable will depend on both average. If this is the plus sign, here is the plus sign. If this is the minus sign, this is the minus sign. But if we look at the variance, even this is the minus sign, and here is the plus sign. Okay, so here, even this is the minus sign, here is the plus sign. Okay, so this is a more general case than the previous one. We extend the situation from one random variable to two random variables. And in the next slide, actually, we can extend this further. We can add a constant before each random variable. And then we get this relation. And then we can even go further. We get an n random variable. It's the same. It's as far as it's a linear function. So this new random variable is a linear function of n random variable. Then we can see this one equals here, and its variance equals this. And this definitely will be given. So you don't need to memorize this, but you know the meaning of this. Do remember here, capital X1, capital X2, they are random variable. They are not constant. Only C1, C2 of this set, these are constant. But capital X1, capital X2, all of these are random variable. Okay? So we look at the last slide from the previous lecture. So we can see if X1, capital X1, capital X2, up to capital Xn is a simple random sample from a population with the mean, mu, and variance sigma square. Do remember this X1, X2, capital X1, capital X2, up to capital Xn. These are random variables. Then, if these are random variables, then we can get the variance of the new random variable x bar. What's x bar? The average of x1, x2, up to xn, right? X bar will be a new random variable. It's just the linear function here. And this time, we take C1 equals C2 equals C3 equals 1 over n, right? So we get this new random variable, and we get it equals sigma squared divided by n. Do remember, sigma x bar is the standard deviation of a random variable x bar. Sigma itself is the standard deviation of a random variable x. X is a random variable. X bar is another random variable. They are not same. Okay? So when you look at it here, do pay attention here. This is x bar, not x. Okay? This is x bar. And the same thing for the standard deviation of x bar. And the sigma x bar equals the sigma divided by square root of n. So I can just draw something for you. It's better. Okay, so we can see if we get a population, this is a population, and for any population, without know its distribution, we can still calculate its average and its standard deviation, right? So here, we didn't make any assumption about this population. It could satisfy any distribution. And we get its average is mu, and its standard deviation is sigma. And if we randomly choose one item out of this, we can denote it by x. So its random variable is x. So if we randomly choose 5 out of this, so I put it as sample A, then we can get the 5 one will be A1, A2, A3, A4, and A5, right? A5. So from this, we can calculate the average x bar A, right? We can calculate the standard deviation SA, right? Then I put this 5 item back to the population. I randomly choose another 5. I call this sample B. If we get a sample B, again we can get a B1, B2, B3, B4, and B5. we can calculate x bar b, SB, right? I can continue this forever. Then, should A1 equals B1 or not? No, right? So each time, the first item is random. So we call this set of data with the random variable x1, capital X1. The second line is x2. The third line, this is x3. So you can extend it to the further case. Then we can see we get a set of x bar. For x bar A, should it equals to x bar B or not? No, right? So they get that small variance. So we learned this is the sample variance, right? So we can use the random variable x bar. So we can see we are more focused on this set of data, x bar. For x bar, I can calculate the new average, right? So it will be mu x bar. In the long run, if I take an infinity sample, x bar and mu x can simplify right as mu. What's the relation between mu x bar and mu x? They should be equal, right? And here we can see this is the original population with the random variable x. And this is a new population with the random variable x bar. So do remember, x bar is a random variable now. When we see x bar, it is not referred to x bar A, x bar B. It's a random variable. And this random variable also has a variance. So we come back to the slides. So we know we get two populations. One is x itself, the other is x bar. And this is the sigma x bar square. So the variance from x bar, that population, related to this one by a factor 1 over n. And the average, they are equal to each other. But the variance difference by 1 over n. So the standard deviation difference by 1 over square root of n. Does that make sense? This is the first round. We will come back to the second round later on. Okay, so this is the summary of this part. Basically, we get the sampling, the discrete random variable, continuous random variable, and get the linear function of the random variables. Then we move to lecture 2. For the lecture 2, basically, we are talking about the commonly used distribution. And here, this is a lot. And we definitely can cover normal distribution, center limit theorem, Bernoulli distribution, Bernoulli distribution, binomial distribution, and see if we can cover Poisson distribution today. Okay, so this is the normal distribution. And we can see this is the probability density function. If a distribution is a PDF is given by this formula. Here it includes the two parameters, mu and sigma. X is a variable, pi is a constant. And it looks like this. Then we call the x, random variable x, has a normal distribution with the parameter mu and sigma square. And we can denote it as a random variable x satisfy normal distribution with the parameter mu and sigma square. And for this normal distribution, and we calculate its mean and variance, and we can get this mean equals the parameter mu, and its variance equals the parameter sigma square. So then we learned the mean and the median before. For this distribution, what's the relation between its mean and its median? You don't need to do any calculations. Just look at the shape. If the distribution is symmetric, what should it be? Equal, right? So its mean and its median equal to each other. And then for this normal distribution, why I talked about it first? Because this one is very important. It can call a Gaussian distribution. This is the most commonly used distribution. And if you only learn one continuous distribution, you should learn the normal distribution. And this is continuous rather than discrete. And when you model, most time it is satisfied, and its mean, mu, can have any value, and its variance can be any positive value. And this normal distribution also the basis for the confidence interval and hypothesis testing. So if you have any questions for this part, you should clear it by this week. Don't wait to revisit it after the Chinese New Year. So if you wait 2 weeks or more, you will forget it. So I changed it a little bit here. Here, I put the disadvantage of the normal distribution. They have a lot of advantages, but it do have its own disadvantage. What is its own disadvantage? We can see this function form. It looks complex, but still not that awful. And if we want to know the probability that a random variable in the range from A to B, then we need to integrate this out and with these two limit boundaries. When we integrate this out, we get a problem. Do you remember the tutorial question 6 in lecture 1? In tutorial 1? That's a linear function. When we integrate out, we can get a formula. Then we plug in the formula, we get the answer, right? It's very straightforward. But here, we don't have a closed form for this part. So when we integrate this out, we cannot get an analytical solution. How we can approach that? We can only approach it numerically. Do you guys learn the numerical method in mathematics 2? Sound familiar, right? So the numerical way is pen to S. I remember when I was a student, that's a long time ago. And if we want to do the numerical, do the integral, basically we draw the function first on scale, then cut that function out with the weight of the piece of paper. Then we can do an estimation about the integral. So if we want to solve it numerically, it's a pen to S. But we can see, if we change the mu, we can see the distribution will be different. If we change the sigma from this black one to this red one, the distribution will be different. The probability from 0 to 1 definitely will change, right? So that means for all the normal distribution, we need to do it numerically. So this is the disadvantage. It looks very beautiful, but hard to use. Then people working on this, and they study this again and again. Finally, they found if we draw the normal distribution in this way, and we put mu in the center, then here I didn't say mu minus 1. I say mu minus 1 sigma, mu minus 2 sigma, and this is the mu plus 1 sigma, mu plus 2 sigma. Then they found the range between mu plus minus 1 sigma is about 0.68. The range between plus minus 2 sigma is about 95, and the range of plus minus 3 sigma is about 99. This is okay, we can do it numerically. It's no surprise. The surprise is this results is independent to the value of mu and sigma. So no matter mu equals 100 or mu equals 0, it doesn't matter. As far as you convert to this way, then we can get the same results. So this proportion with a given number of standard deviations of the mean is the same for any normal populations. So this is the basis for the next slide. Since this area, this probability under the curve is independent to the value of mu and sigma, that means we just need to solve the problem once, right? Then for any arbitrary normal distribution, we just convert it to this form, right? Then we look at the next slide. For this slide and the following two slides, I make a little bit of change, and I will upload the new lecture notes tomorrow. So you can just look at the screen. So our goal is to convert any normal distribution to this unit 1. And we know the property that we have is within a given number of standard deviation of the mean is the same for any normal distribution, right? So we just need to convert it to in a unit of standard deviation, right? So we put dealing with the normal, convert the unit to the standard unit. The standard unit here is just its own variance. So the standard unit will tell how many standard deviation observation is from the population mean. So we know we need to do the unit conversion. And we can see, I think most of you guys already saw this before, either in your GC or in Poly, right? But did you never look at it carefully why we choose this way? Why? We divide by sigma is obvious because we need to get it in unit of sigma, right? And what's the beauty? We put x minus mu. We can see originally the PDF is this, probability density distribution function is this one. If we plug in z equals x minus mu divided by sigma, that means x minus mu equals z times sigma, right? We plug in x minus mu equals z times sigma here. Then what will happen to the sigma square? What will happen? It will cancel. And here we only get a minus z square over 2 left, right? Then we can see for this part, I just keep it the same. So now I ask you a question. After we convert x to z, can sigma choose the arbitrary value? Yes or no? For any probability density function, we have one constraint. The total area under this curve must equal 1, right? So if we put this constraint, then we can get sigma only can equal 1. So we just put this one in here. So we know sigma only can equal 1 if we do this conversion. So this distribution will reduce to this form. We can see it's very straightforward. This is the normal distribution, with the average is 0, and the standard deviation is 1, right? So when we choose z equals this form, we convert arbitrary normal distribution and with the parameter mu and sigma square to one normal distribution, with the average is 0 and the standard deviation is 1. Amazing? then we can see the z is sometimes called a z-score. Here, because we will use this again, I compare these two. So for this normal distribution with the mean 0 and a standard deviation of 1, we call it this is standard normal distribution. And for arbitrary normal distribution, its average can be any value, and its variance can be any positive value. And we can plot it here, and this is its PDF. And for the standard normal distribution, this is a special normal distribution. And its average is 0, and its standard deviation is 1. And its PDF is given by this function, and it always looks like this. Okay? Then we can say we reduce or we can convert arbitrary normal distribution to standard normal distribution. So we just need to do the integral of this one, then we solve the problem, right? So we can see this is Z table. Because we know we don't have a closed form, so we need to do it numerically. So somebody already did this for us, then list the table. So we don't need to do it by ourselves. We just need to refer to the table. So for those who come late, please take the table from me. So we need this in the following part. Anyone need a Z table? The critical question also needs a Z table, so you had better have one. So let's look at the Z table together. So the Z table, it didn't give you the PDF for a certain value. So they didn't say when Z equals 1, what is the function? Because for the continuous random variable, we integrate the PDF from the same limit a to a, it gets 0. So we use the cumulative distribution function. So we can see the shadow area is the probability that from minus infinity up to the value of z. So this is the cumulative distribution function in a continuous random variable. So it integrates from minus infinity up to z. Exactly the question that we learned in tutorial 1, question 6, right? Then we can see we get this one. For this table, the first column is the first two significant number for z, and this top row is the third significant number for z. So if I want to see, look at this table, the value for minus 3.62, I should look at minus 3.6 first, then get this row, then 0.002 here, so I know from the table get 0.0001. Okay? So for the example 1, we need to find the area under the normal curve to the left of z equals 0.47. So what's the first two digit for this z value? 0.4. So we look at the 0.4 first, then the 7.47 here. So we know the value is 0.6808, right? This value, that means we integrate it from minus infinity up to this value. So this area either on its left side or on its right side. Left side. So we can get our conclusion. This is just the answer. So from the table, this is this. So what about z is smaller than minus 3.69, or z is larger than 3.69? So look at your z table. If z is smaller than minus 3.69, what value should we get? We can see when it is minus 3.69, the value will already be 0.0001, right? When z value further decrease, it's safe to say it equals 0. On the other hand, if the z value is larger than 3.69, we can see when it equals 3.69, it's already 0.9999, right? When it's larger than this, it's safe to say it equals 1 directly. Okay? Any questions? Then we look at example 2, which is the z-score corresponds to 75 percentile of a normal curve. So what's the meaning of a 75 percentile? So you need to find a value, and in your data set, 75% of your data is smaller than this value, right? So if this is in a normal curve, how should we understand this? So we can see if this is the curve, and this in this shadow area is the probability that we found the data value smaller than this one, right? So if we found the 75 percentile, what's the area of this? It should be 0.75 or 0.25. Which one? This one? Yes, okay. This is the right one. So after we know the area should be 0.75, we look at the table. Should I look at this one? 0.75? No. We should look at within the table, the closest value to 0.75. So it's either here or here, right? Something in between. In this case, both answers are correct answer. So you can see it equals 0.67 or equals 0.68. You don't need to get another decimal. So either one, 1.67, 0.67 or 0.68, either one is correct. Okay. Get your clicker ready. Okay, so then we can start. So for random variable x satisfy normal distribution, mu sigma square, what's the closest value of z score in the figure? So the figure is here, 1 minus alpha. So 1 minus alpha is from here to here, equals 0.85. So you can key in your answer anytime. Okay, we get a half response now. Then I will give you another 2 minutes. Maybe 1 minute. One more minute. We have 84 people. So now we're waiting another 22 response. One more minute. Clicker, this is a clicker question. This is a clicker question. And we will test the software after this. So because that one is not reliable, so I want to get that row which comes first. This is the triple factor. Sorry, you see the screen of triple? Oh, okay, great. Okay. Then we close the pool. We cannot wait anymore. So this is the correct answer. Okay, I get the data here, and some people cannot see it clear. Anyway, I will analyze the data later on. Here, I just want to go through this together. So we can see we get this curve. And then this part is a 0.85, right? What? Oh. What? Oh, sorry. And so I can see both. Okay, so this is 1 minus alpha. This is 0.85, right? So what's the relation between this area and this area? Same, right? So this part is 0.15 divided by 2. This part is another 5.15 divided by 2, right? This is 0.075. So we know up to here will be from minus infinity up to this value will be 0.075 plus 0.85 equals 0.925, right? Then we look at our z table, find 0.925, and the z value should be 1.44. So the answer D is the correct answer. Okay, we can continue. Okay, so for the next part, it will take about 10 minutes. You guys want to take a break first or go through that part first? Break, okay? 10 minutes break.
Right. So after we see individual G will become. So we get a function of sigma. Right. After we introduce it. Or we get it into the matrix. Anyway, we get a function of sigma. So it must be equal to 1. This is integration value. Either from the one to the information, so that's like we get a function. We need to go to the level of n, the n. In the final form, so we get an n. Right. So even with the a and b, there is no s and s. So the thing is, only between this part, we don't have this and s. But it must be equal to 1. Unless we put it this way, even we know the function is the function. We get an when x is larger than smaller than 0, I don't calculate the value. Yeah. So the thing is, so for this one, I'm going to divide it by 8. Take one. Can you explain it? So we add the value of the this one is minus not this one. Yeah. So the notation here, this is one thing. So we need to be consistent. So if the person has we will have a management. Or we get the thing to compute or anything. The solution, whether different or different, I'm asking something like So basically, yeah, 25 is yeah. The trick of factor
Where's the video then? So on the right hand video.
So we can say big farm is a small and a big farm is a large and a big one is a small. So it will be smaller than big farm. We must have a public yeah,
Okay, so you may receive email about test the new software, and we get a clear here to help us. Please get your cell phone or iPad or any smart device ready. So for the next one, we will test this software first. And for the test case, no matter what kind of answer you key in, you get a 1 mark, you get a 0.5 marks. Okay, so this is the bonus.
Thank
And it's a failure. We come back to our normal show. Want to try some fancy stuff, so you can vote even you are on the bus or in the meeting. It seems that we need more time to test the system. So when I test it in my office, it works, but I don't know what's wrong here. Anyway, we can survive. Okay, so we already go through the normal distribution. So the next part is about the central limit theorem. Central limit theorem, again, we don't request you prove anything. So this is just a part of the central limit theorem. This is about the distribution of x bar. So I already repeated it several times that if you still recall this, so if you still recall this, basically we know that x bar is a random variable. And in the linear function part, we know the relation between mu x bar and mu x, sigma x bar and sigma x, right? And for the central limit theorem, they said for the x bar itself, it satisfies normal distribution. So this here, x bar is a random variable, and same as we showed before. And we get x bar satisfy normal distribution. And with the average is a mu x bar, and its variance is a sigma x bar square. And in the previous slide 35 in lecture 1, and we already know that this mu x bar equals mu x, and we can simplify this mu x as mu. And sigma x bar square equals sigma x square divided by n, and we simplify this symbol by sigma square. So we drop the subscript. So for this one, and we can plug in here, the mu x bar equals mu, sigma x bar square equals sigma square divided by n. So we get the x bar satisfy normal distribution with these two parameters. Okay. So we don't prove it, I just numerically show what's going on. And when I draw the sample, I said I didn't put any restriction for our population. It could satisfy any distribution. So this one, it satisfies something like a normal. This one is a discrete distribution. And this one is a weird distribution. Okay, so the population, here this is population, maybe it's small. The population could be any distribution. But no matter the original population satisfy what kind of distribution, we can see if we get x bar is average of the 5 random variable. Then we can see this is a normal approximation, this dash line. And for this one, it's more symmetric. And we can see this already, the dash line and the solid line overlap to each other. And this one, this bar, is from the discrete random variable. And this dash line is the normal distribution. We can see they fit very well, right? For this one, because the original population is very ugly, if we just take a 5 random variable, it seems not satisfy very well yet. But if we increase the number of random variable to 30, then we can see they almost the same, right? This one, the agreement is reasonable. So here, the rule of thumb is when the random variable here is larger than 30, then we can apply central limit theorem very well. Okay, I said this is a part of a central limit theorem. And we can look at the other part. For the central limit theorem, it makes two statements. One statement is about the average, the sample average. So we already go through X bar. So this is the sample average. It equals the individual sample divided by n. N is the sample size. The other is the sum of the sample observations. So this is random variable, one random variable. The sum of n random variables, sum of them together. For this one, for this quantity, the summation is also a normal distribution. And its parameter given here. The average will be n times mu, and the variance will be n times the sigma square. Okay? Any questions? And the rule of thumb for central limit theorem is when n is larger or equals than 30. This approximation is a good one. So from now on, you need to make a judgment when you see a set of data. This is a random variable or it's an individual measurement. So in other words, this is X, capital X1, X2, X3, or this is just the A1, A2, A3. Okay? So this is one application. We can see at a large university, the mean age of the student is 22.3 years, and the standard deviation is 4 years. So from here, we should know all the students in this large university is the original population, right? And for this original population, we have the average is 22.3, and the standard deviation is 4. Then we look at a random sample of 64 students is drawn. What is the probability that the average age of this student is greater than 23? So here, the first thing we need to think about, what's our random variable? The average of 64 students, or just an individual, the age for individual student? Which one? The age of individual student or the age of a 64 student, the average of a 64 student? Which one? Average, right? So our random variable should be the average of 64 students. Then this random variable satisfies what kind of distribution? From a CLT, it should satisfy normal distribution, right? So then we can see this is the original population. We get a mu is 22.3, sigma is 4. And this is the average of 64 students. It should satisfy normal distribution, right? Then we can get this is coming from here, right? And this is mu x bar, it equals mu. So we put 22.3 here. And they ask larger than 23. So this is 22.3. So this is a normal distribution with the average 22.3, and the variance is 0.25. They ask the probability in this distribution is larger than 23. Okay, so in this distribution, the variance is 0.25, not 16. Then we can see in this one, we calculate the z-score. This is x here 23, and this is mu x bar, and this is the sigma x bar. So we take the square root, we get the sigma x bar, right? When you calculate the z-score, you get x minus mu divided by sigma. all of this must be consistent. You cannot say here is a mu, this distribution is about x bar, and here you plug in sigma x. That will be wrong. If this distribution is about x bar, here must be sigma x bar. Okay? Then sigma x bar equals square root of this. So this is the right of this cutoff value. And from the z table, what we get is to the left. So we need to use 1 minus this value from the z table, and we get the probability is 0.0808. Okay? Too many to digest. So this is a summary for this part, for the normal distribution. And the most important thing is this score. You need to understand the meaning of this score. For this score, we convert arbitrary normal distribution to standard normal distribution. Standard normal distribution has the average is 0 and the standard deviation is 1. And the central limit theorem basically tells you that two random variables, one is x bar, the average of a sample, one is the summation of a sample, and these two random variables satisfy normal distribution, and their parameters are given by this. Okay? Then we can move on. Let's see if my movie works. I like this movie. Why is the voice? Anyway, today is not my day. We can skip the movie and look at this boring stuff again. Okay, so we talk about binary distribution, and if you do a toss, you get a coin, and you randomly throw it up. When it falls down, it can be either the face up or face down, right? So it only have two outputs. One is face up, the other is face down. So if we consider face up as a success, so we can see they only have two outputs. The success is the probability P, and the failure is 1 minus P. And this kind of a trial is called a binary trial. Only two outputs. So for example, if we want to decide we go to Vivo City or Jurong East, then it's okay. But if you said, should we go to the Jurong Point, Jurong East, or Vivo City? Sorry, it's not this distribution. We only have two outputs, successful or failure. Then we can see for this one, if we describe it mathematically, when random variable equals 1, we consider it as a success. When random variable equals 0, we consider it as a failure. So the successful probability will equal this p, smaller p, and this equals 1 minus p. And for all other values of x, 1.1, 2, 3, 4, whatever, the p of x is 0. The probability to get other values is 0. Then we denote this random variable satisfy boundary distribution. And here we can plot this distribution. We can see this is like a bar diagram, and the width of each bar is 1, and the height of this is the value of this probability. For this one, we can see the successful probability is 0.8. Is 0.8. So the failure probability is 0.2. The width is 1. The height is its value. And the mean, and this is its probability density function. And this is a discrete random variable. So based on the formula set B in page 3 in lecture 1, and we can calculate its average and its variance. So it equals, the average is P, the variance is P times 1 minus P. Then we go to the binomial distribution. For binomial distribution, now we just learn binomial distribution. For whatever discrete random variable, you can try binomial distribution. But later on, we will learn the Poisson distribution and the hydrogeometric distribution. The first thing you need to identify if this discrete distribution is satisfied binomial distribution. So to check that, the first thing is each trial must be binary trial. So for each trial, only success or failure. The second thing is the trials are independent. All the trials are independent. And the third requirement is each trial has the same successful probability. If all these conditions satisfied, we can say x be the number of success in the n trial. X will follow a binomial distribution with a parameter n and p. N is the number of trial, p is the successful probability. Okay? Then we can see the probability density function and given here. So for x, the range is from 0 to n. And if it equals other values, no matter it's integer or non-integer, as far as it not equals this value, this PDF equals 0. So this is one example. We take the binomial distribution with 10 trials and the successful ability is 0.4. Then I put n equals 10 and p equals 0.4 and plug in this formula. I can get the probability PDF value for 0 up to 10. For all others, it's 0. Then I can draw this. So this is the distribution for the binomial distribution, and the width of this is 1. The height is its PDF value, and we can see the middle 0 is in the middle of this, not on the left side or the right side. It's just in its middle. We need to use this when we do the continuous correction of the binomial distribution. So for all these bars, it sits in the middle of its value, and the width is 1. Then we can see this is the previous binomial distribution. If we change the parameter, and we can see the binomial distribution will change for sure. Okay? Any questions so far? No? Can you hold a few minutes? We get a critical question. Okay. Now we can see, we get the last example. Let's wait so we can do it slow. Okay, we can see for the binomial distribution, we get P of x equals P random variable equals x, and equals n factorial divided by x factorial n minus x factorial times the successful probability up to x 1 minus p n of minus x. So this notation is a factorial. It equals n times n minus 1 times n minus 2 and times dot dot and times 1. So it starts from n and decreases by 1 until it reaches 1. So for 1 factorial, it equals 1 directly. Okay, you are fast. Then for the 0 factorial, because we don't have a definition for this one, so we define the value of 0 factorial equals 1. Okay, then we plug in this formula and we can get this table. So this is just the factorial part, and this is the exponential, the polynomial part, and the answer should be this term times this term we get here. So here, because I'm in a rush, so I didn't make the judgment. So first thing we can think about, if we get let's revisit it. When you look at this question, so first thing you should know, this is a discrete random variable, right? And we said the probability to have a girl is 0.488. It's not 0.5. Do you guys know it? So girls get less probability than boys. The reason is long time ago, the medical condition is very bad, and the boys, more boys cannot grow up before they die. So they die at a very early age. So the nature just increase the chance to get a boy, to make sure that when you guys go to the adult, you get the equally number of men and women. So you guys should feel lucky. Okay, anyway, so here come back to the question. Is in a two boys family, the two child family, what's the chance that for the first birth we have a girl? So here we don't consider about twins. We just consider for each birth we only have one child. So if we only have one child, we either get a boy or girl, right? If we get a girl, so we consider it as a success. And what's the chance for the first birth we have a girl? 0.488, right? And what's the chance for the second birth we get a boy or we get a girl? Still same, right? So for each time, this is the binary trial, and they are independent to each other, and the successful probability is the same. So in that way, the number of girls will satisfy binomial distribution. So we can use this to describe this. So if no girls, we get two boys. If we first birth is a boy, second birth is a girl, or first birth is a girl, second birth is a boy, we get this. If both get girls, we get this. Okay. Huh? Why is my clinical question? I remember it's there, but anyway, we can do it here. So this is a still clinical question, not a fancy stuff. Okay, so this is a clinical question. Which of the following is not a requirement of a binomial distribution? Okay, one more minute. We get more response than last time. Okay, I will close the pool. You need more time? Okay. Technical problem. I understand that. Maybe you can write the answer to me. Okay. So we close it. The answer is C. C is not the requirement. So the successful probability could be any value between 0 to 1. So in our example, we choose the successful probability is 0.4. And in a baby, that is 0.488, right? All others are requirement. So this is for critical questions, all the data is there. here. Now it is 1. Anyway, we go through this. Go through this one. So the meaning of a binomial distribution, the mean and the variance of a binomial distribution are given by this. And we know for the successful probability, sometimes we don't know, so we need to do the estimation. When we do the estimation, we just get a sample, then the number of successful in this sample divide the number of trials in this sample. So this is the number of success in the sample. This is the sample size. So we can estimate the successful probability from a sample to a population. So you can see this one get ahead. So this is the estimation. And for the estimation, we get the standard deviation. Because if we try another sample, we may get the different results, right? And if we just get a one sample, and we put the successful probability of a population equals the successful probability of this sample, we call this is a point estimation. And we will extend this point estimation in a confidence interval. Here, this is just a point estimation, and we can know this is a very rough estimation, but it's the first order approximation. If we don't have other choice, we can use this one. So the standard deviation of this estimation, sigma p hat, equals this. And this can be approved, but I will skip it here, and I will not test you either. And in principle, it should be the successful probability of a population. But when this quantity is not available, we just use the successful probability of a sample. This, from this step to this step, this is the approximation. When we run our choice, we use this approximation. If we know the true value of a p, we should use its true value. Okay. Then we look at one. Let's see. This is the last sample that I will go through today. A quantity, you guys can read it. I want to find my water. I remember I bring it. So basically, we can see the quality engineer take a random sample of 100 stills and found 92 of them meet the specification. So they want to estimate the proportion of that day. So we can treat all the product from that day as a population. So basically, he get a sample. The sample size is 100. So we can see in this sample, the successful trial is 92, and the sample size is 100. So we can get the p hat equals 0.92. And also find the standard deviation in the estimation. So basically, we calculated the standard deviation of this p hat. It should equals this, right? But we don't know the value of this. So we approximate this value from here. This should be approximately equals. So we get this one, get this. Okay. Last point, approximate a normal approximation to the binomial distribution. So if you look at the discrete distribution, this bars, this is the binomial distribution with the number of trials is 100 and the successful probability is 0.2. And just remind you that the width of this bar is the number 1. And this bar, the exact number is sit in the center of this bar. So for each bar, this value is 16. So this bar starts from 15.5 and at 16.5. Okay? Then we overlap a normal curve with this binomial curve. We can see they're almost the same, right? So that means at a certain condition, we can approximate binomial distribution by normal distribution, right? Because for binomial distribution, the calculation is very tedious. If I increase this to 1,000, then you need to calculate forever. We have an example I can show you later on. So then we can see if random variable x satisfies binomial distribution with the number of trials is n, the successful probability is p, and the number of successful trials is larger than 10. The number of failure trials larger than 10. Then we can approximate this binomial distribution to a normal distribution. No matter binomial distribution or normal distribution, they should have the same average and the same variance, right? So we just put the average of the binomial distribution to here, the variance of a binomial distribution to here, then we get our normal distribution. And the estimation of the successful probability also satisfies normal distribution, and it is given by this. So when we apply this binomial distribution to normal distribution, do remember that a binomial distribution is a discrete distribution. Normal distribution is a continuous. So if we approximate binomial distribution to normal distribution, we need to do the continuity correction. And what's the goal to do the continuity correction? The goal of continuity correction is to keep same probability in binomial and normal distribution. Sorry. So for this one, we can see if a fire coin is tossed 100 times, and we can get this binomial distribution, right? And we can see if we ask the probability from 45 to 55, and with the 45 and 55 included, that means we want to get the probability 45, 46 up to 55, right? If we want to get the same probability, that means we should get the same area. And in the normal distribution, we should start from 45 or 45 or 44.5. Which one? We should, in normal distribution, if we want to get the same area, we should start from 45 or 44.5. 44.5. We should end at 55 or 55.5. 55.5, right? This is the continuity correction. So in the normal distribution, we should start at 44.5 and end at this. The reason is we include the 45, and we want to include the whole bar, not just a half a bar. In the next slide, we said the 45 and the 55 is exclusive. If this is exclusive, basically we remove the equal sign here. We just get the small sign here. In this case, we remove this bar, and we also remove this bar. This time, the normal distribution should start from 45 or 45.5. 45.5, right? It should end at 44.5. So the continuity corrections, you don't need to memorize any rules. These rules extend or retract half grid. They're very tedious. Basically, you just draw it, keep it in mind. You need to get the same probability in binomial and normal, then you can get the integration lower boundary and upper boundary easily. Okay? Any questions? So for the Poisson distribution, I will cover it in lecture 5. So in next week, we will talk about question 5 in tutorial 1, question 5 and 6 in tutorial 2, question 1 and 2 in tutorial 2. So we will talk about 5 questions. Question 5 in tutorial 1, question 5, question 6, question 1, question 2 in tutorial 2. Okay. Sorry for all the technical problems.